Okay, welcome to the seminar today. I can see a few of you got your coats on. The potential of the room is about increasing. Okay, so rarely, if ever, do you need a collective noun for laureate fellows. But today, this morning, the announcement of the laureate fellowship means we have 2 new laureate fellows in the room. One being Hivoye, our very own Hivoye. Congratulations. And the other, quite nicely succinctly, is our speaker, Anya Redding. Who was awarded the Georgina Sweet Laureate Fellowship this morning. And give a shout out to Geodesy, a friend of the school, Matt King. You also of the University of Tasmania was awarded a laureate this morning. So it's been a good day for earth sciences. We'll call him 5,2. So Anya hails from the University of Tasmania, Professor Anya Redding. Her background, just go if you don't mind, a little potted history. She was undergraduate at Edinburgh University, moved on to a PhD at the University of Leeds in the UK. Then worked for the British Antarctic Survey for a number of years before moving as a lecturer to the University of Edinburgh, where she was recruited by our talent spotter extraordinaire, Brian Kennett, back in 2000 to come to RSES. And you spent some time here as a research fellow and then a fellow and left in 2006 to go to the University of Tasmania, where she is now a professor of geophysics. So Anya leads the Compute Antarctic Research Group at the University of Tasmania, working on machine learning techniques in addition to studies involving geophysical modeling and inversion. Current focus areas include the detection of changes in the major outlet glaciers of East Antarctic Ice Sheets and Southern Ocean wave climate. She's has a diverse career, but has been very well known for her work in Antarctica. She's the director of the GRIT facility, great acronym, GRIT. I'll let her explain what GRIT means, and also a co-lead of the Australian Centre for Excellence of Antarctic Science. And I'll cut it short there. She's going to talk to us today about computational and geophysical adventures at East Antarctica. Over to Anya.
Thank you very much, Malcolm. Good afternoon, everyone. Before I start, I'd like to organise quite a large group of co-authors, most particularly Tobias Stahl and many PhD students and researchers with whom it's been my absolute pleasure to collaborate with. So East Antarctica, this is an example of kind of the research challenge that we sort of set ourselves. Because I and many others approach East Antarctica kind of through seismology. This is kind of an example of what we know about East Antarctica, or what we knew. So the left-hand image is 2004, the Shapiro and Ritz-Waller model, and the middle image is 2020. So you can kind of see how far we travelled in that time, and the aim of these adventures is really to take the next step, to move kind of in an equivalent way to how we moved from 2004 to 2020, but hopefully do it a little bit faster. So the reason we want to kind of move faster for Antarctica is, of course, that the Antarctic continent is overlain by ice sheets, and those ice sheets are changing fairly rapidly. So West Antarctica, on the left of the screen, locations such as the Quakes Glacier, the Larsen embayment on the north of the peninsula there, they're losing mass rapidly. West Antarctica is underpinned by a kind of a foundation of continental blocks, a little bit like sort of New Zealand. East Antarctica, completely different. It's an ancient assembly of cratons, fold and thrust belts, somewhat similar to Australia. Both of them are covered by great ice sheets, and we want to find out more about the earth beneath and the earth ice interactions. And there's kind of an overarching endeavour to understand how if the Y of East Antarctic, or the Y of Antarctic ice sheet change, is the warming ocean and the warming atmosphere. Undoubtedly, the how into the future is how the ice sheet interacts with the earth beneath. It's being forced by the ocean, it's being forced by the atmosphere. But whether it'll stick or slide, how it will respond is very much contingent on the interactions with the earth beneath. The grey areas on the screen there are of particular interest because they're locations where the subglacial basin is below sea level. So there is potentially a kind of runaway effect that we have a great concern about should the ice sheet cross, or should the ocean ice sheet boundary cross that threshold. So the way that some of the things we care about are captured in the little graphic at the bottom of the screen here. So the ice sits on the earth beneath. The bed might be frozen, or it might be thawed. There might be subglacial water, and that ice is flowing. And some of those hows that I talked about pertain to ice deformation physics. They pertain to basal sliding, bed geometry, and geothermal heat flow. And definitely those last three things come really from the earth science realm. Okay, so making progress, and in particular focusing on East Antarctica, because that's the area of Antarctica that where there's great Australian interest through Australian Antarctic Territory. We have great ice sheets, a very high volume of ice. And the character of the ice sheets is a little bit different than in the West. In the West, we've got this big ice shelves. We've got a great number of sort of outlet glaciers. So we really care about the sort of deep cut channels that these glaciers are carving, and the capacity of ice to move rapidly through those channels. To state the obvious, the other thing that is a big issue is the fact that the place is huge. So we have to somehow develop, progress knowledge in a manner where we can get knowledge across a big area from very sort of localized field observations, and that really leads us to seismology. So seismology, especially passive seismic data, is able to bring very high temporal resolution. It's able to pick up movements of glaciers over a big area just simply by putting a seismometer onto the ice or in the ground adjacent to the ice. So we're really in a realm of using ice quakes in a similar way to understanding the Earth plate tectonics through earthquakes. And we hope to do so using relatively light logistics, so that we can cover multiple locations in a reasonable time frame. The international context of this is the International Polar Year. We're tracking towards the 5th International Polar Year in 2032. And that big contrast between the 2004 sort of very blurred rendering of the continent of Antarctica. The reason that it really leapt ahead in those 20 years was the year before. So that's a really sort of significant motivation for different nations to work together. So what what we're sort of resolving to do, if you like, is to better resolve the Antarctic continent and better resolve many aspects of the ice sheet that pertain to Earth-ice interactions. The mode of operation is really a combined approach. So our group, the group that I lead, goes under the name of Compute Antarctic. And the reason to lean on the compute is really to get the understanding, to get the progression of knowledge at scale. There's a significant emphasis on data collection, but the field deployments are tailored to the computational approaches. So I'm going to talk about today field deployments, ice quakes, that key ice bedrock interface zone, a little bit of geothermal heat, and a pointer towards some future endeavours. So Malcolm mentioned the GRIT facility, so that the all-important acronym is Geophysical Research Infrastructure for Antarctica. It was a sort of group challenge to come up with an acronym that didn't involve any A's or any E's, because there were way too many of those in Antarctic life. So we took some components from previous ARC LEAF grants, including one in collaboration with Veravoya, and we were lucky enough to be awarded a sort of major grant at the end of 2023, which enabled an expansion across seismic instrument sets, magnetotelluric instrument sets, and GNSS instrument sets. So all the instrumentation is polar rated, and the idea is that we can deploy those instruments sort of in two-person teams, because that's kind of helicopter friendly, and basically get ahead with the data collection. So the images here, that's Tobias upgrading one of the GNSS instrument sets. So that component is overseen by Matt King, and myself on the seismology, and Kate Sallow overseeing the magnetotelluric instrument sets. Okay, so this is Antarctica as we all think of it in our group, so without ice, and you can see here the BedMap 3 compilation. So this shows in a bit more detail the contrast between the highlands and the big subglacial basins. And we've been rolling out deployments over the past couple of seasons. In particular, so looking basically at the ice sheet, at the ice bedrock interface zone, at ice quake processes, and all the sort of various layers in the cake beneath the ice. So a few geographic locations which I'll be referring to as the talk progresses. So Casey Station is just about here. So that's if you fly from Hobart to Antarctica, you land close to Casey Station. Concordia Station is in the sorry, put the label in the wrong place. Concordia Station's there, that's possible. And major glaciers. The Denman Glacier was the subject of the Denman terrestrial campaign, and the Vanderford-Totten Glacier is also a location of great interest. So we have the kind of immersive polar experience in the seminar room today. This is kind of what you end up doing if you do seismology in Antarctica. So the instruments are established with a solar panel, which is usually well above head height when it's installed, and then you go away and leave it for the winter, and it snows, and you come back and it's buried by sort of many more feet, hopefully, but sometimes actually several meters of snow. So the first job is to chainsaw down to the instrument box, and to retrieve the data. So we are restricted in putting masts or anything that might tell us where the instrument box is buried, because we don't want to measure the seismic signal of the mast or the marker cane waving in the wind. Of course, it's incredibly windy. This location is sort of 25 knots of wind, that's sort of nearly 50 kilometers per hour of wind. And that's myself, and that's field guide digging down and extracting the data. So we use some of the techniques that you'd use to find people who've been buried by avalanches, so avalanche transceivers and things, to sort of re-find the box. This solar panel was, yeah, way up high, but it's, as you can see, it's almost completely buried. Didn't mention aircraft. One of the amazing spin-off benefits of Antarctic research, at least from my point of view, because I'm a complete av geek, is flying in amazing aircraft like this Twin Otter aircraft. So 18 years ago, I think, we were in this room just when I'd been offered the position at the University of Tasmania, and Malcolm just told a story about the perils of Antarctic research and the fact that I had to spend 2 weeks in a tent in a blizzard with a dude called Psycho. And the very same Psycho, yeah, so 17 years later, is now a senior logistics person for Australian Antarctic Division, and he happened to be leading the Inland Traverse. So the Inland Traverse is a very big deal for the Australian Antarctic Division. It serves the Million-Year Ice Core effort, which is near to Concordia. And the Traverse team basically trundle many hundreds of kilometres across the ice cap to take the fuel and the heavy gear to the Million-Year Ice Core drilling. And Psycho kindly took a couple of our very lightweight instrument sets and installed them, did a fantastic job. Little side story, between them, the team did not have a compass on them. So, or even actually a handheld GPS, because they are in the realm of much bigger instrument sets. But fortunately, they had a very talented groomer driver who was able to draw on the snow an exactly grid north set of tracks. So they were able to align the seismometer north using this, I think it's multiple millions of dollars of piston bully groomer instead of a handheld compass or a GPS. But anyway, this is the return of Psycho, the very same Psycho. So all that seismic installation experience that he got 20 years ago came into its own. Okay, so these are the those glacier locations zoomed out. The Denman Glacier system, the Vanderford-Totten Glacier system, that's the traverse route. Those are the installations that Psycho and team put in. And yeah, so Denman terrestrial campaign over a couple of seasons. Tobias and Kate Selway and myself deployed or uplifted seismic data from those locations. So just to get your eye in, this is mostly beneath the ice. The green patches are high ground, the dark blue patches are channels, canyons beneath the ice, and the dark red colours are where the ice is flowing rapidly. So we're trying to get the instruments in as close to the sort of rapid ice movement as possible. And the idea is really to establish what the glacier processes are using ice quakes, a little bit like one might establish that with tectonic events, and then drop down to a smaller number of instruments and sort of monitor those processes and we're tracking towards telemetry. We don't have telemetry right now for the seismic data, but that's where we're tracking. The other location of interest here is a seismic array deployment that we put in a few years ago in collaboration with Hervoya, and that is sort of tailored to understanding the seismic wave field, not so much the structure beneath the ice, but learning about the seismic wave field and how that changes over the calendar year in Antarctica. A couple more field pictures. This is the Bunger Hills camp, so our little tents are here. Some of the camp infrastructure there, the kitchen tent, communications, radio room and things like that in here, and yeah, beautiful expanse of freshwater sea ice which stays frozen throughout the Antarctic summer, where we can land aircraft and basically operate. So that's the camp from which we access the Denman Glacier region. On the right here, Perfect Picnic. One of the aims of GRIT is not only to deploy instruments and collect data, but also to train the new cohort of field researchers. I may not go on forever digging holes in ice or chainsawing holes in ice. The reason I put this up is so PhD student Liam Askey-Doran, this was his first helicopter flight. So this is his first field location. So this the bubble, the speech bubble above my head is something along like, Liam, it's not always this good, because we did have a perfect day out. The Liam's first day out, and in the background there, that's the absolutely mighty Denman Glacier, which is emptying a huge part of the Aurora subglacial basin. You can see through these quite narrow constrictions. So the processes happening at the Denman Glacier are really important in terms of understanding the how the East Antarctic Ice Sheet is evolving. A few more sort of field pics to get the flavour. So this is a very far south site. You can see it's pretty unfriendly. That's spindrift blowing off the ice there, and then the ever present job of digging instrumentation. That's Colin Sarah, who's the postdoc on the magnetotelluric work, and also the recipient of the Golden Shovel Award from the Bunger Hills camp 2 years ago. Okay, so glacier processes. This is what we're aiming to do. Glacier systems are full of different kinds of processes. So we have ocean noise, we have sort of processes that are a little bit like some of the tectonic processes, stick slip, crevasse crack type processes, but also very different processes like water movement, some really quite high energy resonances when you get water going down channels, some very enigmatic low frequency signals, which are quite interesting, and there's a few that you can only describe in sort of onomatopoeic terms. If you're on a big snow surface or camping on a snow surface, certainly every now and then you hear just this kind of whoomp sound, and of course all those get recorded. It's kind of a cacophony, kind of a seismic symphony of all these noises. So the challenge then is to extract those key signals from the symphony. It's almost like sort of reverse engineering a symphony to understand the processes from multiple signals happening at once. And the first endeavour, or most of the examples that I'm going to show you come from sort of legacy data sets. So we're sort of processing some of the legacy data sets whilst we deploy the new instruments. So this comes from the Willans ice stream, which is in West Antarctica. It's one of the big players in terms of feeding ice into the Ross ice shelf. And the computational hero carrying out this work was Rebecca Latto, who was a master's student with our group. And so sure the supervisors in the room can empathise. It was I was feeling really bad because the Willans ice stream is an absolute beast. Terrible place to cut your teeth in terms of seismology, but Becca did this amazing job. So full credit to Becca. So legacy deployment by Paul Wingberry and Sridhar Anandakrishnan and colleagues. So yeah, it was our task to take those seismic signals and kind of create a new approach. So we came up with a two-part approach. Ross Turner was one of the players here. So he comes from an astrophysics background. Astrophysicists are very used to dealing with multiple signals at once and extracting key signals from a noisy background. So that was great, a great combination. So the two-part system that we established is basically, firstly, an event detection, basically form a catalogue. And we're using quite a sort of basic short-term average, long-term average approach, but in a kind of group search way across multiple combinations of frequencies, and then supervised learning approach. So this is some results from the Willans ice stream. There's a bit of a tidal control, but not a complete tidal control. Better show some waveforms. So this is the STA LTA algorithm working across some waveforms. This is the big basal stick slip. So the time here is in minutes. So this is like a really long period stick slip. These events are pretty evident without any sort of machine learning, but some other events will, most of the other events are not evident, which begs the question actually for this kind of work, exactly what is a seismic event? Where does it start? Where does it stop? So we had to make a bunch of decisions about how to handle that. And the aim was really to create a systematic reconnaissance. So we can basically go to any glacier system, any ice stream, and sort of start from a baseline set of processes. So yeah, these big stick slips. I mentioned the more like tremor signals, and this is a very small sort of local ice crack. And these basically happen on top of each other all the time. So it is quite a job to separate them out. But yeah, I'm really proud of Ross and Becca and co for really kind of cracking that challenge. So the way that this was done was through an unsupervised learning approach. But firstly, rather than working on the raw waveforms, calculating feature attribute sets. So the different colours here indicate different sort of attribute groups, either some network metrics and waveform metrics, spectral characteristics, some polarity things. So basically anything that you can calculate from a time series, and then separating out the signals based on those attributes. In most cases, you just kind of take the results and run with them, but we wanted to understand how the different groups of signals partitioned themselves if we took different decisions about how many groups we wanted to use. So there's two groups at the top with subsequent allowing the set to split itself into more groups as you go down the line. And for this glacier, for this ice stream, kind of 10 groups came up best on various metrics. So that's what we used in the work going forward. So the insights that came out of this with these sort of bivariate plots, give us domains that enable newly recorded events to be sort of sorted into the domain and hence identified. And just to pull out a couple of things from these different spatial and temporal plots. Big burst of a certain kind of signal over 2 or 3 days. We worked out that that corresponds to a big sort of noise burst from the ice shell. And this lower right plot is the sort of daily average. And there's a kind of a thermal related set of events coming out at a certain time of day that shows in the light blue there. So we're sort of starting to be able to do that reverse engineering to kind of pick the individual instrument noises out of the cacophony of the ice stream symphony. Okay, so this now moving on is work by Jared Magyar, who was an honours student here in mathematical geophysics. And Jared's basically taken this methodology and developed it. And what we're looking at here is results from a very small glacier. This is quite close to Davis Station. And it sort of exemplifies the seismology challenge. So if you are working in the Swiss Alps, for example, you tend to have your seismic sensors all over the glacier, and you can expect to have a kind of well-behaved seismic network with the events sort of in the network somewhere. Whereas in the East Antarctic context, you have a sort of a little array and with the events all around the outside of the array. So it kind of calls upon a different set of seismology tools. And it also, you end up in some quite heated tangles with reviewers from the Swiss or the European Alps, because they're expecting you to have hundreds of sensors and the sensors to be widely distributed. It's the reverse. So anyway, Jared's done a great job at rolling this workflow forward, and you can see some rather beautiful stacked events here in the different categories, and using unsupervised machine learning again to form the event groups. And this glacier is a bit better behaved, so it was also possible to use some sort of template matching type event, template matching to refine the catalogue. So Jared also implemented some pre-component matched field processing, so some kind of classic array processing techniques to get event locations. Not very surprisingly, a lot of the events come from the sort of tongue of the glacier, but there's also this sort of intriguing kind of cluster of processes. So the Sausdal Glacier is kind of a smaller, kind of the opposite end member to the Whillans ice stream. So it's really helped us refine the techniques. And these are some more sort of insights. The grouped events by date, time, tide, back azimuth. So these sort of event groups. You can see here that tide has very sort of little effect on the Sausdal Glacier events, but the time of the year has quite a big effect there, starting to really active through January and then dropping off. So yeah, we very much want kind of year-round recordings to understand that sort of the really sort of active summer period when the glaciers start really changing and sort of catastrophically changing in some cases. Second study by Jared Magyar, these are grounding line processes at the Totten Glacier. So this is Lord Dome, Casey Station's about here. The yellow line is the grounding line, so that's where the ocean is impinging under the ice shelf, and the ice shelf starts floating. So again, this is a legacy data set where we have just a few seismic instruments and we're interested in the seismic character of the glacier environment. And then again, the idea is to sort of get a baseline picture of what events are active and then monitor how those events change over time. The Totten has some really kind of characteristic repeating ice quakes. So it looks like there's a sort of a kind of stick slip patch. And the stick slip patch kind of evolves a little bit over the summer. So the you're really kind of repeating waveforms, kind of uncannily similar waveforms. And yeah, the sort of basal stick slip mechanism happening there. And the reason that that is important is because if there's a particular asperity for a glacier, it's not if that asperity is broken out somehow, it means the whole glacier could be kind of unroofed, sort of uplifted, even if it's quite a small change in the sort of grounding environment. So the small changes, it's very sort of the non-linear geometry could have a big effect on the way that the glacier changes into the future. The next group of studies involve the ice bedrock interface. So this is work by Ian Kelly. And yeah, the big question here is looking at the ice stacked over the sediments beneath and asking in that key area where the ice sits on top of the unlithified sediments, is the ice frozen to the sediments, or is the ice on a sort of slippery, muddy base, and therefore really very sort of prone to sliding? So will it stick or will it slide? And the tool that Ian's really progressed is using horizontal to vertical spectral ratios to characterize the layers in the ice bedrock interface. Ian's looked at multiple different methodologies for characterizing these HVSR curves. He's also looked at sort of multiple or big ranges of different parameter spaces. So in terms of the work that Ian's done, there's been two sides to it. Firstly, synthetic studies. So this is the body wave model, synthetic sensitivity testing. So across a whole range of different parameter spaces, ice depths, sediment characters, how do those HVSR curves change? And the key thing that Ian's looking for is a peak shift. So that peak turns up at different frequencies depending on the ice bedrock interface sediment character. And yeah, it's that shifting peak that is the diagnostic part of the waveform. One thing that Ian looked at very carefully was what affects these HVSR curves. So these are peaks from different times. These are peaks from stations across Antarctica, again, legacy data. And you can see the blue through to the red colours are different times of year. So HVSR techniques have been used quite a lot in Australia for looking at depths of cover over crystalline basement exploration, that kind of thing. And they're kind of renowned for being really unreliable. So this kind of starts to shed a bit of light on why they can be unreliable. It is not a good place to model the whole waveform. The whole waveform shifts around depending on the seismic wave field that's the HVSR is being calculated from, but the peak shift is a consistent metric. So yeah, Ian's really progressed our understanding of how those HVSR curves can be used reliably, robustly. So lots of things start feeding in together. We want to progress that. We now have like a really compelling reason to understand the seismic wave field and how we can use that in a sort of in passive seismic mode to be able to cover the continent or important parts of the continent quickly. So this is the sort of ragged spiral array that we installed over the last couple of years. And it brings together work by Martin Gall a few years ago and Ross Turner. And yeah, that's our sort of next job, really. And of course, spiral arrays are quite attractive in terms of looking at inner core phases. So yeah, it'll be exciting to work with Heravoya in terms of some of the inner core insights. So yeah, this is multi-geophysical installations in the last year. So that's putting Mancero training NEOM to install MT instrumentation. And the idea is to use the MT instrumentation in tandem with the seismic data. The MT is particularly helpful where we've got salt water impinging underneath those glacier channels. Okay, so the last group of studies that I'd like to share are some statistical work on geothermal heat flow. So this is, of course, a really important boundary condition for ice sheet modelling. We really want to know the spatial variability of the heat that's being supplied, how that heat is shaping the ice sheet from below. And geothermal heat flow has lots of contributions. So we have the kind of the basal heat flow from the deep earth, and we can add to that some sort of more patchy heat flow from heat producing elements. So granite batholiths, for example, inject or add a good deal more heat, and it'll get really confusing when you have sediment refracting the heat flow and groundwater and ice. So one of the reasons that I wrote a review paper on this topic a few years ago was that there are lots of different heat flow models out there, and some of them are quite different in different ways. And there was a sort of kind of research meme around the fact that we didn't understand the differences between the models, which was terrible because we actually do understand why these models are different. But it is actually quite hard to reconcile the addition to the heat producing part of the heat flow map to the basal load with the resolution that we need for with the resolution that we need. So you can see here the basal heat flow adding the heat producing envelope. So if you drill and if you measure heat flow, you kind of get somewhere on this kind of bumpy surface, which absolutely doesn't lend itself to kriging. And then the narrative gets rather confusing because people are trying to ground truth a surface that has lots of peaks and troughs with spot measurements. So one of the ways forward is to use an empirical approach. So using a sort of statistical means to map heat flow onto locations where we don't have heat flow measurements. So one can either use a global reference or a well sort of constrained reference like the United States. So I I'll skip over a little bit of detail here, looking at the time. But the bottom line is that Tobias came up with this very nice heat flow map. Some really important high spots. That's underneath the quakes Glacier, the so-called Doomsday Glacier. Yeah, very fast changing part of the West Antarctic Ice Sheet. And for East Antarctica, everything's a little bit more subtle, and in many places we're sort of below the needed resolution. But the Tobias came out with a robust result with some wide uncertainty bands, and he's also working with Marie Lersing, who interestingly came out with a machine learning supported result, which was with narrower uncertainty bands but less robust. So this gave us quite an interesting set of comparisons to make, and we really learned a lot through those comparing those different data sets. One of the big outcomes from the AQ1 model, so Tobias's work, was looking at which input data sets were important, and there's some quite involved work in terms of which data sets were most sensitive. And in general, the AQ1 model was rather insensitive to the exact choice of input data, which is good news. But we did learn quite a lot about how to integrate kind of multiple layers of data. So these are satellite results on top of the seismic derived data like seismic wave speed and some satellite gravity metrics such as shape index bed topography. So the best integrative anchor data sets are the seismic derived ones, which just proves the awesomeness of seismology, which sort of takes us to back where we started. So this is our sort of resolve to resolve. So we're deploying stations in really key places like that inland traverse, and the deployments with the Psychos team. And we've just recently added to that a potential collaboration with a French group to sort of deploy along the French traverse from Dumont d'Urville into Concordia, which covers sort of similar ground. So we're sort of targeting the data collection, combining that with statistical approaches, which enables us to sort of handle various factors that are sort of strictly sub-resolution. So this is a bit of the data collection along the Casey Davis coast. So this is not particularly focused on glaciers, but where there are outcrops, especially because we want to co-deploy GNSS stations together with seismic stations. So these are long duration stations, and looking at combining improved seismic topography maps with some constraints on the lithosphere boundaries that come from again kind of multivariate statistical approaches. So the rather kind of beautiful ghostly map on the right here is some lithospheric boundaries which come out of a kind of Boolean logic approach, kind of mapping the likelihood of lithospheric boundaries. So work right now to start bringing those approaches together. In terms of actually making that happen, international partnerships are really important. So this is the Laureate Fellowship. The Delphi got funding. So we've been working on the Aurora subglacial basin, and part of the Laureate Fellowship is to basically expand some of the methods that we've been talking about, together with the network of airborne radar data across these kind of key subglacial basin areas. And the map on the left shows where you have subglacial basin areas overlapping with extreme surface change. So either an air temperature increase or an ice surface acceleration, ice mass loss, elevation drop. So our kind of areas of peak interest are where the ice sheet's changing fast, and also there's an overlap with the submarine basin. So yeah, immediate future partnerships expanding coverage into the Wilkes subglacial basin. I mentioned the partnership with the French National Antarctic Programme, and also we're looking at some partnerships with the adventure tourism operators. Actually, Ian Kelly was part of the field team that deployed some stations supported in the last year by adventure tourism, which is you certainly get more whiskey at your field camps with the adventure tourism, luxurious experience. And yeah, so that's where I'll end. So yeah, addressing the need for rapid knowledge generation for East Antarctica, and the idea is using those computational techniques and the field data in partnership. There's a range of insight areas from the top to the bottom. The ice sheet's telling us about the glacier processes, the sort of more detailed seismology telling us about the ice bedrock interface zone, and then really focusing on the deep earth variability beneath the ice. Roger's group obviously looking at attacking that from a different direction, so looking forward to those conversations. And then those partnerships with the different national Antarctic programs, and also private logistics starting to support a bigger rollout of those instruments. Thank you.
You, Anya. The floor's open for questions.
Hey, I thought it was really interesting how you display some of the seismic data in frequency domain. Is it possible to deconvolute those peaks and map those back to specific seismological events? Has that been explored at all?
With the
I forgot the acronym. I think it started with an H.
oh, the HVSR.
Yeah.
So the HVSR is actually, my apologies, just background noise.
Oh, I see.
So it does work for yeah, it does work for some distributed source type noise. In fact, the back in 2013 we sort of rolled out a similar set of data collection, working with an industry partner in the Australian mainland. So that was for an exploration endeavour, and we got some beautiful HVSR curves, but they were actually missing a frequency band. And it turned out that we could fix that by this is, you know, in the outback, by driving it a tree round and round in circles. So it's sort of noise, it's kind of background noise, but sometimes it's sort of slightly engineered background noise to fix some frequency bands.
Okay.
So I'm looking forward actually to driving snowmobiles around in circles.
Thanks, Anya. I had a related question about the HVSR. You see a really nice time variation here. And I just wonder if you could clarify what you think is causing that. Is that because something about the ice is changing, or something about the noise is changing?
So pretty much definitely it is the noise that's changing. So Antarctica, it's basically the sea ice changing. Ian's done some pretty careful work on the how those peaks kind of lose amplitude when the sea ice around Antarctica sort of freezes. So what the sea ice does is it moves the ocean noise a long way offshore.
Yeah.
So it is impacted by the sea ice. It's also impacted by the wave climate, the sort of storm climate of passing oceans, of passing ocean storms. So HVSR is, as you might know, is really kind of compelling as a passive method, because you only need to deploy the instruments for a few days. So that sort of enables quite a big coverage, especially using kind of smart solo node type instruments, enables quite rapid coverage potentially. But you need to manage this sort of the fact that the signal's really apparently quite unreliable. But I think we've really made some progress in understanding how to manage the reliability of the signals. And with our inversion heads on, and we've made some use of the coffee infrastructure that Malcolm and the team have developed, making the inversion schemes where it's not the shape of the waveform that we're modeling, but the exact frequency of the peak. And that's the robust part of the system.
Thanks, very nice talk. I just wonder about the heat map that you showed. It's very clear that the West Antarctica is more heat flow, right? So I just wonder, what does it mean for the internal eye temperature? How different part of Antarctica, like the temperature within the eye or just near the base of the ice sheet?
So this is showing only the component of geothermal heat flow. There's some very nice work by Frank Patton from Belgium. And he has and his group have basically mapped out what that looks like from the point of view of the ice sheet. And kind of, it's a bit paradoxical, but as the ice sheet gets deeper, as you go further into the interior, the ice sheet is actually warm based. So because there's a bigger depth of ice, it's warm at the base. So often thawed actually, so above zero by the time you get down deep. And then kind of in the kind of outer zone, it's still frozen by the time you get to the base. So this is kind of it looks like a kind of bullseye with warmer ice in the middle and colder ice around the outside, and it seems a little bit paradoxical, but the that's come from the glaciology community. So I didn't show it in this talk, but we are working quite closely to try and get those sort of interdisciplinary angles on ice base temperature and the basically the flow of heat energy through that ice bedrock interface zone better understood. It's kind of interesting because in terms of thermal conductivity, the thermal conductivity of ice sits between the different options for the sediment compositions. So this is the key thing. So sandstones, mudstones could be either side of ice conductivity. So that means it could refract either way. So it means accounting for topography and these sorts of effects, the kind of the way that the heat is focused or defocused by bed topography is really non-trivial, because we need to know what the rock's made of. And so geoscience is it.
Thank you. Very nice talk. I think, remember somewhere in your talk, you mentioned this, very complex wave field, in this region. Just curious, like, how far do you think you might, it is from, you can model this kind of wave field, and what are the major challenges actually? Seismic wave field.
Yeah, so the I think it's kind of a sort of heuristic problem, really. You just kind of like going to a forest with a microphone. And in fact, I've got a colleague who works on machine learning of bird calls being a proxy for biodiversity. So one forest is going to sound different to another forest depending on what bird calls you can hear, and so it's the same. I mean, even within the East Antarctica, one glacier actually has quite a different character, sings a different song to the next. And I think you just basically go there, put the instruments in. The systematic thing, it's really good to have a sort of systematic analysis process, because then you can more closely compare one glacier system to another. But I think it's kind of fine that they are different, and that's part of it, just the way that you expect different groups of birds in different forests, really. On that matter, on that note, there's a science art festival in Tasmania, in Hobart. So if you're considering a winter break, do come to the Beaker Street Festival, which is in National Science Week in the middle of August. And our group, I don't have the slide, but our group is putting on, working with a very talented group of artists, as the Denman Glacier Seismic Dance Party. So, those sounds from the Denman Glacier have been sonified, converted into dance tracks. The festival is intended for kind of adult age group. So nominally, I kind of know this because I'm on the board of directors, but nominally they're 18 to 35 age group. But if you feel that you may be, in your heart of hearts, still in the 18 to 35 age group and want to go and dance, it should be, it's over 2 nights. Should be an amazing experience. So yeah, do consider a winter break to Hobart and that science festival. There's a whole heap of events on. Yes, and interestingly as well, so if I go to the field, I can't kind of help but lie on the ground and sort of get a bit of a feel about what the ground feels like. And the different locations do feel different. You can, if you're camping in Antarctica, you can feel those different events, seismic events, really, really easily. You get a kind of feel for what it's like. And the people putting on the seismic dance party at Beaker Street Festival were sort of like, oh, hang on, how about deaf people? If deaf people want to come and dance. So there's going to be a whole lot of things called haptic vests. So if you don't use your ears to hear, you can feel the glacier vibrations through the haptic vests, and apparently it's quite confronting feeling. So yeah, I can't wait.
Well, it's probably good to end on an intergenerational and interdisciplinary note there. So I think we've probably reached our time limit. So let's thank Anya again. I think we might be having some morning, afternoon tea outside, possibly. Anyway, thank you, Anya.
Thank you for the invitation.
I had no idea what there is afternoon tea.